We're looking at, so far, the whole lesson that we were looking at last week, we were looking at different ways to graph the lines, right? We were looking at what pieces and stuff like that. We were finding concavity, we were finding intercepts, we were finding mins and maxes and those type of things. The one thing that came up that we couldn't necessarily find was what happens when the thing doesn't exist. What's going on at that place? Or what's happening as we're going to infinity? And in those situations, we need to use limits. Now, we've covered some of this before, and actually these two problems we've done before. So what we did before was the first thing you want to look at when you're doing limits is let's factor things out. Let's look at, can I simplify the problem down? But what was the very first thing you should always do in your limits? Just plug the number in and see what you get. Because sometimes that works. So if we plug in 1 to this, I'm going to get 1 minus 1 over 1 minus 1, so 0 over 0, which doesn't work. So one of the methods that we look, let's see if we can factor. This one, we actually can factor. So I can take the x out of the top, and I get x minus 1. And the bottom is the difference of squares. So it's x minus 1 and x plus 1. So this goes down to, because I can cancel out those two, and I'm left with x over x plus 1. And now I do the limit again. If I plug 1 into this, I get 1 over 2. And that's my answer. Okay, so one of the nice ways, if we can factor things out, that's great. Do that. The next one was going to infinity. Now, infinity had a little bit of a different rule to it. So it wasn't, if you could factor, great, go ahead. But when we're looking at the infinities, we were dividing by something. So again, first thing, if I look at the top and the bottom, these are both going to infinity over infinity, which doesn't work. So I need to do something else. So we're going to take each of these and we divide by the biggest exponent on the denominator. So in this case, I'm dividing by x squared. So now I have 1 minus 1 over x squared and 2 plus 1 over x squared. And then as the 1 over anything goes to infinity, as 1 over infinity, it goes to 0. So I'm left with just 1/2. So this, if we looked at this graph, it actually just came to a point and there was a hole there. So it goes to 1/2. This one is a horizontal asymptote. As it's going to infinity, it's going to 1/2. So both of those give me information about the graph. Okay, and that's why we're going back and looking at limits, because the ones we did before were very simple. They worked, they were polynomials for the most part. We could do these types of things to simplify them down. However, if I wanted to do a problem like this, ln of x over x minus 1, if I wanted to find the limit as x goes to 1 of this, if I plug in 1, this goes to 0 over 0, which again, doesn't exist. So it's like, okay, how do I find my answer? How do I find this limit? Well, L'Hopital, we spent a month debating how to spell this guy's name because there's like 4 different variations of his name online. And we ended up not using the S. It was L'Hopital. But it was like the one little thing out of writing this entire calculus book. We literally debated how to write L'Hopital's name because we use it a lot. Okay, so it's one of the actual, like a very useful skill, especially when you get into Calc 2, because it allows us to find limits of functions that we would not necessarily be able to find. Yes. Oh, yeah. Huh? I was not this book. I wrote 2 calculus books. We did Calculus 1A and Calculus 1B, and then we did a Calc 2 book. So we actually wrote 8 calculus books, actually, when it broken down to it. So that was my job that I got let go of last week, that they closed the whole division. So I'm like, need to find other things. So yes, there's a calculus book out there with my name in it. So how do we go about doing this? So L'Hopital's rule basically states that if you take the derivative of the top and the derivative of the bottom and do the same limit as that, you'll get the limit of the original problem. So basically we're looking at how does the function change over how does the function change? And if we divide the changes, you actually can get the original answer. There's a whole big long proof to it. I'm not going to bore you with it. So what the key piece to this is, L'Hopital's rule has to be in this format. It has to be in a division format. When we're taking the derivative of it, we're not doing the quotient rule. We're taking the derivative of the top and the derivative of the bottom as separate pieces. And then we're doing the limit as it goes to that. This works when it gives me an indeterminate form to begin with. So if it does not give me an indeterminate form at the beginning, this will not work. Okay, so the first couple indeterminate forms we looked at actually with this problem here, or actually with this problems, was 0 over 0 and infinity over infinity. Those are two indeterminate forms, which means those do not exist at the beginning. So if I look at that original problem that I just did, if we had the limit as x goes to 1 of x squared minus x over x squared minus 1, was it minus x or plus x? So what's the derivative of the top? What's the derivative of the bottom? And if I plug 1 into that, I get 1/2. This is exactly what we originally did. The notation you use to do that is that. It's a little equal sign with an h over it. That means I use L'Hopital's rule to go from step 1 to step 2. Okay. A little bit simpler to go through and do. But it only works if it gives you an indeterminate form to begin with. So if we get something that works, that's why I said always plug in the number first, because if it works, we're done. We don't have to go through and do this. And actually, the answer you get using L'Hopital's rule will give you the wrong answer at that situation. All right, so let's look at this one. So we've got ln of x over x minus 1. So if I plug 1 into this, as we've shown already, that's going to give me, because ln of 1 is 0 and 1 minus 1 is 0. So it does give me an indeterminate form. So we're going to make f of x is ln of x. So what's f prime of x? What's the derivative of ln of x? 1 over x. And g of x is x minus 1. So what's the derivative of x minus 1? This is 1. So now I'm going to find the limit as x goes to 1 of 1 over x over 1, which is 1. And if we look here, this is the graph of that problem. And if you go to 1, it's undefined. But if you notice the limit, as it's getting closer and closer to, it's basically going to 1. So L'Hopital's rule allowed me to fill in that hole and understand what's going on at that equation at that point. Because if I took the derivative of it, I would get a value that doesn't exist at that point. It's like, okay, what's going on? Is it a vertical asymptote? Is it going to 0? Or is it going to a value that we're going to be able to put in? And that's where using this is going to help me fill in those holes. Okay, so or know that I'm going to have an asymptote, which is a possibility. That makes sense? All right, good. All right, try this one. Oh, I should switch back over. Huh? There we go. Try that one. All right, so what's the limit of e to the x over 2x? Well, the top still goes to infinity, right? This is the same thing we started with. Okay. What's the bottom going to? Also infinity. Okay, so what do you think we should try now? Do it again. L'Hopital's rule never stated you can only do it once. So if you look at this problem, the top's never going to change. E to the x is always going to be e to the x. However, if you notice the bottom went from x squared to x, if we do the derivative of it again, so we do the second derivative of each, now that bottom is just 2. The variable's gone. So now I can do the limit as x goes to infinity of e to the x over 2, which is just infinity, over 2, which is just infinity. So as it goes to infinity, it's going to infinity. So the reason why it matters is because it really depends on which one's going to infinity faster. Because if I flip this problem over and I did x squared over e to the x, it would have ended up being 2 over infinity, which goes to what? 0, because anything on the bottom, as the bottom's getting infinitely large, it's going to 0. So, but it would have started off as infinity over infinity. So that's why you can't go, oh, infinity over infinity is like 1, or goes to, we don't know that. It could technically be any of those situations. So that's why we actually have to figure out some other methods to be able to break it down to solve it. So you can do L'Hopital's rule more than once. Do one more in here before we go on to the next one. So back when we originally did the limits, we did a problem like this. Sine of x over x. And when we did this problem, notice you can't factor it out or anything like that. We actually did what was known as the squeeze rule. This one we looked at what's going on the top and the bottom and what was getting squeezed down to at the end. However, we now have L'Hopital's rule. So let's see if we do L'Hopital's rule, what's going on as it's going to infinity. Or actually, wasn't it? Hold on a second. It might not have been infinity. It might have been 1. Or was it 0? This one wasn't infinity. This was 0. This was 0. So if I plugged in 0, I'd get 0 over 0. So find me, do L'Hopital's rule on it. What's the derivative of sine of x? Cosine of x. What's the derivative of x? 1. So as it's going to 0, it's going to 1 over 1, which is 1. And that's actually what we originally found when we originally did this problem. All right, try this one. Right, but you put the second one. Keep the first one, change the location, and put the second one. Actually, don't know. I didn't look at the answer. It's possible. Change this, clean that up, make it a fraction again. Okay. Okay. Yeah, you're right. You keep change before you read it. Oh no, go back here. You keep change. Put the fractions together. when you get the fraction over a fraction, which you should get, do the keep change flip to actually put them together. Right. This one first. Oh. All right, a square root of x one we see a lot. Have that in your note card somewhere so you don't have to go through every time to do all the steps for it. So we have the limit as x goes to infinity of ln x over the square root of x. Using the Hospital's rule, goes to the limit as x goes to infinity of 1 over x over the negative 1 over 2 square root of x, which we're going to change again. So I've got 1, or sorry, yeah. Oh, it's not negative. I'm doing integrals. I spent a whole bunch of time last week doing integrals, and it's backwards, so you can do the negative side. So yeah, positive. Sorry. So we get 2 square root of x over x. So we have 1 over x times 2 square root of x over 1. Which gives you that. That's the keep change flip. Now, if we plug in infinity into this again, I still get infinity over infinity. So we've got to do it again. So this time f of x is 2 square root of x. So f prime of x is 1 over the square root of x. Yeah. And g of x is x. G prime of x is 1. Supposed to infinity, right? Yeah. So I get 1 over the square root of x, which is 0. Or if I paid attention to the book, is the same thing as that. You didn't have to do it again. Because that's x to the 1/2. So if you do x to the 1/2 minus 1, you get the 1/2 in the bottom still. So you could have simplified it down, but it doesn't make much difference. It still works out the same way. So we get 0. All right, one more before we go on to something else. Well, not something else, just another type of these problems. This one's going to pi. Also notice that this one has the little symbol next to it. What does that mean? Right, so this one's coming from the left side. In terms of L'Hopital's rule, it makes no difference. So none of your steps are different in that respect. to how you're going to do the problem. I had to think about it. So it took me a second to think about it because I wasn't actually thinking that first. And nobody got it right. What was the first thing I told you? Plug and pi. You do not. Sine of pi is 0. And cosine of pi is -1. Which is 0. Because it goes 1, 0, -1, 0, +1 for cosine. Can't do L'Hopital's rule on this one. If you can plug the value in, L'Hopital's rule fails. That is why the very first thing you have to do is plug the value in. Yeah. Now, if you had done L'Hopital's rule, you'd have ended up getting cosine of x over sine of x. And if you had plugged in pi to this, you'd have gotten 1, sorry, -1, because we just drew that, over 0. But since we're looking at it in terms of the left, the sign is getting smaller and smaller. So this goes to infinity. But that would be wrong. Okay. So Be careful. Always with limits. Plug your number in first. You got lucky. And that's the thing. It's like sometimes, like, it's like you can do a rule a bunch of times wrong and get the right answer eventually, but it's not necessarily like what. And honestly, even if you had gotten to this point and did L'Hopital's rule again, this is not an indeterminate problem. So that goes to something. So you have to figure that piece out. So when we're looking at them, so you're indeterminate. I think I deleted them. Hold on. Nope. I didn't put it all on one screen. Hold on. I'm going to get a nice little screenshot of all the indeterminate forms. These are indeterminate forms. If you get any of those situations, we can't do the limit as stated. We have to do something else to it to clean it up. So, and right now we've looked at so far, we've done that one and that one. The next one we're going to do is that. Everybody got them written down somewhere? All right, so now the indeterminate form of 0 times infinity. What was the first thing I said about L'Hopital's rule? L'Hopital's rule has to be what? Has to be a quotient. It has to be dividing. It's f prime. It's f of x over g of x. We have to have those two things. If I'm multiplying, I don't have that. Okay. So I've somehow got to take my equation that I've got and change it into a form that's going to give me division before I do my derivatives. So like this problem here, I can't say, oh, let me just take the derivative of ln of x and get 1 over x. I can't do that yet. It's got to be in terms of a division problem before I can do L'Hopital's. So the question is how do I change x ln of x into a fraction? Have we got an idea? What's the derivative of 1? 0. That's not going to help me. So how can I rewrite x? Because like ln of x, I'm not going to get much out of, right? ln of x, there's not much I can do to it to make it a fraction. Technically, I could do the same thing I'm going to do to x with it, but it's easier to look at the x. So I have to do something to it and then undo it to keep it back at the same, right? So if I did 1 over x, that's changed the problem, correct? But what if I did 1 over x? I flipped it twice. Is that x? Because I would, if I did keep change flip, right, I had 1 over 1 times x over 1, right? So I can change this problem, the x ln of x, to ln of x over 1 over x. This, I will tell you, is the hardest thing to like wrap your head around. Okay. And this is, again, it's one of those things like, how can you use the skills you learned from algebra to manipulate a problem, to put it in a way that you can use it to do other things? So, oh yeah, first thing we always have to check, if I plug in zeros to this, I'm going to get 0 times negative infinity, which we don't know. So it fits the format. All right. Is it in a format that I can do L'Hopital's rule to now? Good, so do it. You're welcome. All right, what's the derivative of ln of x? 1 over x. What's the derivative of 1 over x? Negative 1 over x squared. Just bring down the negative 1, subtract the negative 2, goes back down to the bottom. So I have 1 over x over negative 1 over x squared, which ends up giving me negative x, which goes to there. You can start to see how things are building on themselves. All right. Let's do another one of those. Let's do another multiplication. Try this one. I will tell you, this is the type of problem that you're going to see more often with the multiplication. A lot easier than your longest one. Try to remember what cosecant is. Go back to cosecant. Wait. Yes. Change that. All right, since everybody's basically, forgive me, the same mistake. Or actually, you two both did it. Cosecant is 1 over sine. So this problem, as stated, is sine 5x over sine 3x. And now we get 0 over 0, so I have to do L'Hopital's rule to it. So what's the derivative of sine of 5x? What's the derivative of sine of x? Cosine of x. But we have to do the chain rule because we have a 5x inside. So what am I multiplying the sine of 5x or the cosine by? 5. So it's 5 cosine 5x. Don't forget to put the 5x back inside. And the bottom is going to be 3 cosine 3x. Now if I plug in 0, cosine goes to 1, not 0. So this becomes 5/3. And no, you cannot cancel that out and get the answer. Okay, that would be wrong. I figured I was going to get to see at least somebody try that, but most of you didn't get to remember that cosecant 1 over sine. All right, let's look at another one of the indeterminate forms. Subtraction. So subtraction is one of the weird ones because a lot of times people think, oh, it's infinity minus infinity goes to 0, which would make sense. However, just like we had infinity over or 0 over infinity, it's a matter of which one gets there first. Because if the first infinity, if it's infinity minus a large number, that's still infinity. If it's infinity minus a large number, that would be, or infinity, or a large number minus infinity, that would be 0. So you could have different possible outcomes because of the way infinities work. This is what makes life difficult with infinities. So, same concept happens though. Even though I have subtraction, I somehow have to make it a fraction. Because if I don't have a fraction, I cannot do the Hopital's rule. So, not every problem you're going to get in subtraction, you're going to be able to do this method with. You might have to do other methods to find it. But ones with fractions kind of already there, we can. So this goes back to remembering how you actually do your fractions. How do I put these two fractions together? Okay, so what's going to be my common denominator? Yes. So I have ln of x and x minus 1 on the bottom. And then in essence, I'm going to multiply this one by x minus 1 and that one by ln of x. Okay. So if I plug 1 into this, I'm going to get 0 minus 0 over 0 times 0. So I get 0 over 0. Okay. So again, every time you make a change, try it. Because sometimes that change is going to fix the problem for you. Okay. So in the first one, I got 1 over 0 minus 1 over 0. So I got infinity minus infinity. This one, I'm getting 0 over 0, still in indeterminate form. Now I get to do the Hopital's rule. So again, to the top. So what's the derivative of the top? 1 minus 1 over x. Which, since I'm going to have this as a fraction, I might as well clean this one up. So that's going to be x minus 1 over x. What's the derivative of the bottom?
Minus 1 over x plus.
How did you do it? Okay. I missed the piece you said at the beginning, so it's fine. So we've got the derivative of the first, 1 over x times x minus 1 plus ln of x times 1. Again, let's clean this up a little bit. So I've got x minus 1 plus ln x ln of x over x. So I'm actually going to show it to you both ways, with that not cleaned up or with it cleaned up. So if I don't clean this up, if I didn't clean it up, this is what you'd have. You'd have 1 minus 1 over x over 1 or x minus 1 over x plus ln of x, right? Kind of messy. What you can do in a situation like this is just multiply every single part by x. Multiply by your denominator. Okay? And then multiply by my denominator, I'm going to get x. X over x is just 1. That's just x minus 1. And that's plus x ln of x. So that's one way to clean it up after the fact. When we're looking at this one where I've already cleaned it up, you'll notice they're both divided by x. Those are going to cancel each other out. So you get directly back to the x minus 1 over x minus 1 plus x ln of x. However, the problem still is I'm still going to get 0 over 0. Okay? So I still have to do another L'Hopital's rule. So this one down the bottom ended up being 1 minus 0 plus ln of x plus 1 over x times x. That became the 1. That's there. That's there. For those that are trying to figure out how I got to 1 plus ln of x plus 1. Because x ln of x, you have to do the product rule. So now I have 1 over 2 plus ln of x, which if I plug in 1, 2, I get 1 half. Makes sense? I know it's a lot of little steps. It's a lot of places. In essence, the L'Hopital's rule is a lot of manipulation. Like, how do we change it to get it to the way we want it to look? Yeah. Yeah. It was right there. Okay. All set? Okay. All right. Try this one. I'm seeing all the different ways we can try. I'm not- So that we could do that. Okay. It's fraction. I don't know if it's gonna help you. But it's a fraction. That's a fraction. Basically what that is. So that. Oh, try something, try. When I'm looking at a problem, I don't want to change, it, right? You're the closest that with high. That didn't change the problem. Did I do that? I changed the problem, right? Can I do that? That didn't change the problem, right? Okay. Because basically I multiplied it by 1, x over x. Can I do that? Yes? Okay. So that right there goes to infinity, right? That's minus 1. The question is, what does that do? Be infinity over infinity, right? So I can't do that. But we already kind of did that problem. Look back at your notes from earlier in class. What did e to the x over x go to? We did e to the x over x squared was the original problem. But then when I broke that down, I ended up doing e to the x over x in the middle of it, right? Which ended up going to what? It went to infinity. So that's going to infinity. So in essence, this is infinity times infinity, which is infinity. So we did, remember the rules of limits, I can break it apart. I can do the limits of pieces. So in essence, I did the limit as x goes to infinity of x times the limit as x goes to infinity of e to the x over x minus 1. I was able to do it in the pieces. So my guess is you'd have gotten stuck probably in a derivative loop at some point. But sometimes, like, everybody says, these are the types of things that I find in math is fun. It's a puzzle. It's like, okay, I've got this. How do I get it to a way that I can use it? Now, I will say that's what a lot of people find completely annoying about math. Because you've grown up always being told there's always one right answer. You do this, you get the right answer. That isn't the way math is. That's the way arithmetic is, and very simple math. But most math is designed to make you think. It's designed to figure out how do you take these problems and solve them with what you've got. How can you manipulate it in a way that's going to get you an answer? And that's what this is. That's all the L'Hopital's rule is. Is like, we know we have to get it into a fraction. How can I get my problem into a fraction so I can do it? And sometimes you have to do crazy things like this. You were close. He divided it by x and he stopped. It's like, that's why I put that first. It's like, it's close. So it's a matter of which way do you need to go. Okay. So, all right. I think we got a couple more. All right. I think we did, let's see, did we do them all so far except for the last 3? Let's go back to my rules. So we've done that one now. We've done that one. Yep, the 3 power rules. All right, so these are the power to a power. So we can have 0 raised to 0, infinity raised to 0, or 1 to infinity. You would think 1 to infinity is 1. But it's not. It's actually an indeterminate form. Because a lot of times it's not 1 down the bottom. It's something going to 1. So the question is, does it get to 1 before it gets to infinity? In which case, if it does, then it'd be 1. If it doesn't, it could be infinity. If the number is coming from 1 from the other direction, it's coming from the greater than side, it'd be going to infinity. If it's on the other side, it'd be going to 0 because they're fractions. So it's a matter of where is it coming to 1. So that's why that is an indeterminate form. All right, I won't make you try this one by yourself first. I'll help you with this one. Then I'll give you a harder one to try on your own. Because I seem to like to do that. All right. So we have this function here, right? So let's look at this. I have an x in my exponent, right? So I have a power in the exponent. If I plugged in 0 to this, what do I get? So if I plug in 0, I get 1. But if I plug in 0 to cotangent, I believe that goes to infinity. Yeah. Cotangent of 0 is infinity. So I get 1 to infinity. So what do we have as a method to get the cotangent out of my exponent? So let's rewrite this problem. If I do the natural, that's a horrible natural log. So basically the whole problem. I would get ln of y equals cotangent of x ln of 1 plus sine 4x, right? Yes? Okay. What's cotangent?
Sine over sine.
What's an easier way to write that?
1 over tangent.
It's just 1 over tangent. So I've got ln of 1 plus sine 4x over tangent of x. If I did the limit of this one, this piece over here, I can just ignore. Because there's no x in the problem anyway. For right now. So we're going to ignore this piece over here for a second. We're just going to do the limit of that. Not going to ignore it for the entire time. We're going to come back to that. All right, if I plug in 0 to this, I'm going to get 0 over 0. So I need to do L'Hopital's. All right, so find me my derivative of the top and the bottom. All right, so if I plug 0 into this, what do I get? Well, if I plug 0 into 4 cosine 4x, I get what? Over 1. If I plug 0 into secant x, I get secant is 1 over cosine. So I get 1 over 1, and squared is just 1. So using L'Hopital's rule, I get 4. Okay, that makes sense? All right, but I didn't find the limit of the original limit of y. I found the limit of ln of y. So what we found was the limit as x goes to 0 of ln of y is 4. So how can I rewrite ln of y to get y? I would do e. E ln of y is just the y, right? So if I did e to both sides here, that's my answer. So actually, this e is technically out here. So I raise both sides to the e. So the answer is e to the 4th. All right, last brain teaser for the day. I'll give you a hint. You need to use e's and ln's. In some way and form, you're going to have e's and ln's in your problem.
Oh, okay. Not the way it was.
We did earlier. We did that earlier. So go back to that. You actually think this stuff was I don't know what that means. All right. So what some of you've tried is basically doing exactly what we did in the last problem. Which is fine. This does work. Totally works. So we actually did that problem already today. What was the answer to that? That was it. We did it. So now we have the ln of y equals 0. And if we raise the e of both sides, we get y equals, which is the answer. The way the book did it, to show another way to do it, let's just do this. Was the e and the l x is just e ln of x, because that would just be x. And then you have e to the x ln of x, which we already did. So, because in essence, this piece right here is just x. Because the e and the ln would cancel out, you'd be just left with the x. And you're still left with that piece up top that we did already. So that was 0. So you still get e to the 0, which is 1. So both ways work. All right, and that's brain teasers for the day. I will see you on Wednesday. Oh no, Thursday, sorry. My other class is Monday, Wednesday. Don't worry, because I tell them there, like Thursday.